This video is all about mathematical modelling with trigonometric functions. Whenever we have a real-life situation that can be assumed to be repetitive, oscillating, periodic, so something like a pendulum going from side to side to side to side, or a Ferris wheel going around and around and around, or whether the tide coming in and out and in and out, or a wave going up and down and up and down. All of these situations are repetitive, they oscillate, and they're periodic. And so because of that, we can model them with trigonometric functions, whether that's a simple trigonometric function like 5 sine x, or whether it's a more complicated trigonometric function that's a combination of different trigonometric functions that we saw in previous videos, how we can then rewrite that as a single trigonometric function. We're going to do 2 examples in this video. Here's the first one. We're told that the water level in a river is modelled using the equation h equals 2 cos 30t plus 5, where h is the depth of the water in metres and t is the number of hours after midnight. Part A says finds the minimum height the water reaches and when this occurs. The minimum height. So what is the smallest that this can be? Look at the trigonometric function here. I know that the smallest that cos can be is -1. Look at the cos graph. It starts at 1, goes down to 0 at 90, down to -1 at 180, back up to 0 at 270, goes back up to 1 at 360, and so on. The smallest it can possibly be is -1. Therefore, the smallest that can be is -1. So the height would be 2 times -1 plus 5 is 3. The minimum height is 3 meters. When does that occur? Well, now let's think about when does the cos graph equal -1? At 180 degrees. So when the inside part here, when 30t equals 180. So when t is 180 divided by 30, which is 6. Remember, t is the number of hours after midnight, so 6 hours after midnight is 6 o'clock in the morning. That's the first time when we would have the minimum height in the river. Part B says to find the maximum height the water reaches and when this first occurs after midnight. So let's think about the maximum that cos can possibly be now. The maximum it can be is 1. So therefore the height would be 2 times 1 plus 5, which is 7 meters. When does that occur? Well, I can see that it occurs when the angle is 0 or when the angle is 360. So when 30t equals 0 or 360, dividing both of those by 30, 0 divided by 30 is 0, 360 divided by 30 is 12. So we have 0 hours after midnight or 12 hours after midnight. 12 hours after midnight, so midday is the first time after midnight when the height reaches its maximum of 7 meters. And then for part C of this question says to find after how many hours the height will be 5.5 meters. So let's use our model to find when does h equal 5.5. So I'm going to take my equation, make it equal to 5.5. I'm then going to subtract 5 from both sides. I'm then going to divide both sides by 2 to get cos by itself. I'm now going to do cos inverse of that. So cos inverse of 0.25, and I will get I'll get 75.5 as my first answer. Or, using the graph, I can get the next answer. So I had 75.5 from here. There'd be another answer at 360 minus 75.5, which would be at 284.5. There would be another answer at 360 plus 75.5. But I'm just going to give 2 answers here. So I know that 30t has to equal either 75.5 or 284.5. If I divide both of those by 30, I find that t would equal 2.52 or 9.48. Those are the 2 values of t. So this is 2 hours. The 0.52, if I multiply that by 60, that's going to tell me how many minutes that is. So that's 2 hours and 31 minutes after midnight. And this is 9 hours. And again, multiply the 0.48 by 60, and you'll get 29 minutes. Those are the 2 values of t when the height in the river is 5.5. And hopefully you can see all of that makes sense if I show you this graphically. So we can see that the maximum height was initially 7 when t was 0 at midnight. It went down to its minimum height of 3 meters after 6 hours. So that was the 6 o'clock in the morning. It then went back up to its maximum height of 7 meters after 12 hours. So that was at midday, and so on. We saw that it had the height was 5.5 meters after 2 hours, just over 2.5 hours, and again after 9.5 hours. So hopefully our calculations there make sense. Right, this one is a slightly longer, more complicated question, but having done the previous few sheets of work, this shouldn't be too difficult. So we're going to break this up. Parts A and B are nothing new. We did questions like that in a previous sheet. So I'm going to just remind you how we do parts A and B. I've already shown most of my working out here. I have expanded out the r sine theta minus a. I've then compared the sine theta there and the cos theta there, which allowed me to see that the r cos a had to be 2, and the r sine a had to be the 1.5. I've then turned this into a little right-angled triangle there, with r being the hypotenuse. The adjacent I know is 2. The opposite I know is 1.5, and then a little bit of Pythagoras allowed me to work out r, and a little bit of SOHCAHTOA allowed me to work out a. So all of that allowed me to turn this complicated expression into a simpler single trigonometric function there, which is really useful because now I can just look at this and I can see what its maximum and minimum would be really easily, because I know the biggest that sine can be is 1. And so the biggest that 2.5 sine could be is 2.5. So the maximum is 2.5. Now to find the value of theta when that maximum occurs, let's think about the trigonometric function sine. It has a maximum of 1 at pi over 2. So if this bit on the inside here equals pi over 2, that's when the maximum would occur. So theta minus 0.64 equals pi over 2. And then if I add 0.64 to both sides, I find that theta is 2.21 radians when that maximum occurs. Right, now moving on to part C and D of this question. Bearing in mind, we've just shown that 2 sine theta minus 1.5 cos theta can be written as 2.5 sine theta minus 0.64. We are now told that Tom is modelling the height of seawater, h meters, on a particular day using the equation h equals 6 plus 2 sine 4 pi t over 25 minus 1.5 cos 4 pi t over 25 between the values of t being 0 and 12. Now, just compare that equation with what we found in part A. I hope you can see that the 2 sine t and the minus 1.5 cos, those bits match up perfectly with what we had in the part A of the question. The only difference is we don't have a theta anymore. We've got this 4 pi t over 25. And we've got this plus 6 at the beginning. So, what I have done to help me for part C and D is I have rewritten this equation in a simpler way. I've just copied the 6 down. And then I've used my answer from part A to replace this, the only difference being instead of the theta, I've written the 4 pi t over 25. That's the only difference. Now that's useful for part C because it says calculate the maximum value of h. So I know that the biggest that sine can possibly be is 1. So therefore I will do 6 plus 2.5 times 1 is 8.5. So I know the maximum height is 8.5 meters. I now need to say when that occurs. So thinking about the sine graph, when do we have a maximum on the sine graph? It's when the angle is pi over 2. So if that 4 pi t over 25 minus 0.64, if that equals pi over 2, we have a maximum. I'm then going to add the 0.64 to the pi over 2. That's going to be 2.21. And then I'm going to multiply by the 25, which gives 55.27. And then divide both sides by the 4 pi to make t the subject. And we get the value of t as being 4.40. So 4.4 hours. That's the value of t. And I could turn that into hours and minutes if I needed to. Part D of the question says, calculate to the nearest minute the times when the height of the seawater is predicted to be 7 meters. So I've taken my equation for the height of the seawater, which was this thing, and I've made it equal to 7. I've then subtracted the 6 from both sides. So 7 taken by 6 is the 1. I've then divided both sides by the 2.5. The 1 divided by 2.5 is 0.4. I then did sine inverse of the 0.4, which gave 0.412 on my calculator. I've then just used the sine graph to get the second solution. I know that this here is 0.412, so then I just did pi take away 0.412, and that gave me the second solution of 2.73. If I wanted to, I could draw the graph further and get more solutions, but I don't need to for this question. All I've done after that then is I have added 0.64 to both of these answers, and I got 1.05 or 3.37. I then multiplied them both by 25. I then divided them both by 4 pi, so that I got the values of t being 2.09 or 6.70. Those are the values of t. The question did want the times though, so I've then turned those values of t into times. The 2 is 2 hours, the 0.09, multiply that by 60 and you see that it's 5 minutes. So 2 hours and 5 minutes after midday is 2:05 in the afternoon. And then the 6.70, we've got the 6 hours. The 0.70 times 60 is 42 minutes. So 6 hours and 42 minutes after midday is 6:42 in the evening. And again, just to represent what we've just done there, what we've just worked out, here is the full equation of what I just found here. I rewrote it to be in this form to make it easier for me, so that I could say that the biggest it can be is when this is 1. So I had 6 plus 2.5 times 1, which gave me the maximum of 8.5, which we can see there. I was then able to find when that occurred because I thought about the inside, and I know that this would equal pi over 2 at a maximum, and then I solved that to get the 4.40. We also used that to find when the height was going to equal 7. So the height here being 7, reading across, you can see we get the values of t as being the 2 hours and 5 minutes and the 6 hours and the 42 minutes. So that is how we can use trigonometric functions to model situations that can be assumed to be repetitive and oscillating.